Imagine reviewing your continuous integration pipeline on a quiet Tuesday afternoon. An external contributor opens a pull request against your public repository. Absolutely no code has been merged. No human has even approved the changes. Yet behind the scenes, an unsafe workflow silently picks up that pull request and runs the stranger's code. Worse, it's running that code with your base repository privileges, effectively handing an unknown entity the keys to your infrastructure. So how does this happen without a single merged commit? Nothing has been merged yet. So where did the privilege come from? We need to establish right up front that ordinary pull requests do not automatically receive repository secrets. By default, standard pull requests originating from a fork operate in a heavily restricted, unprivileged sandbox. GitHub actually defaults to safety here. The privilege we're talking about isn't just handed out by the platform, it's inadvertently granted by the workflow architecture itself. It usually happens when an engineer, with the best of intentions to automate a task, accidentally engineers the vulnerability right into the pipeline. To understand exactly how this breakdown occurs, we have to map our architecture into two distinct zones of trust. Over on the left, you've got the untrusted fork. This is where an external contributor is proposing changes. On the right side is the trusted base repository. To make this real, think about what actually lives over there. Your production secrets, your AWS OIDC roles, NPM publishing tokens, Terraform state credentials, and your trusted cache. Between these two zones lies a persistent trust boundary. Maintaining the integrity of your pipeline means keeping these two zones strictly separated at all times. The failure almost always starts at the very top of your YAML file, specifically with how a workflow is triggered. Let's look at the standard pull request trigger. This is the safer default for evaluating untrusted fork code because it runs with explicit read-only permissions and heavily isolates the execution. Now contrast that with a workflow configured to use pull request target. This trigger fundamentally changes the context. It runs directly from the base repository's default branch context. It is highly privileged. Now, pull request target isn't inherently unsafe. It is entirely appropriate and necessary for trusted metadata work, like labeling a PR, but it was never designed to build, compile, or execute untrusted fork code. Using a privileged trigger is not a vulnerability on its own. The event name is not the bug. The trust boundary you cross next is. The critical failure happens when a workflow uses that privileged pull request target trigger, but then includes a step, usually using actions/checkout, that is explicitly configured to fetch the pull request's headref instead of the base branch. The exact moment that step completes, you've just invited untrusted material across the boundary and handed it the keys to your base context. Once that untrusted code enters your privileged environment, the execution of the malicious payload rarely sits plainly in the workflow YAML file for you to spot. The execution hides in the repository files themselves. Think about a routine YAML step that simply runs npm install. The attacker doesn't need to touch your CI file at all. They just add a malicious pre-install script to a package.json file in their pull request. When your privileged workflow installs dependencies, it unwittingly runs contributor-controlled code. The exact same concept applies to modified makefile targets, altered test suites, or customized build scripts. This dynamic creates a massive false sense of security during code review. Reviewers often approve pull requests simply because the workflow YAML itself hasn't changed. But reviewing workflow definitions for suspicious commands is completely insufficient if that workflow is designed to dynamically retrieve an untrusted execution environment. The YAML may only be the doorway. If the workflow pulls in the attacker's commit, the attacker controls the environment the second any build, test, or install command is invoked. When that environment is compromised, we have to look practically at what assets are at risk. First up is the GitHub token. The impact here depends strictly on the permissions granted to that token in your repository settings or workflow file. Next, any repository secrets made available to the job. It's a very common misconception that log masking protects these secrets, but redaction in logs is not a sandbox. A compromised process can simply base64 encode a secret in memory and exfiltrate it silently to an external server via standard web request without ever printing its literal value to the log console. Finally, your trusted default branch cache state is entirely exposed. If you're finding this explainer helpful for auditing your own pipelines, consider subscribing to DevOps Corner. Let's move on and look at a much more insidious attack vector that results from this exposure. Let's meticulously map out how cache state exposure turns into a severe escalation path. Think of this as a sequence of events. Imagine it's late Friday afternoon. Step 1. An untrusted influenced run, mistakenly operating in a privileged default branch context, executes and writes a malicious poisoned cache state. Maybe it's a backdoor dependency tucked into a cached node modules folder. Step 2, that initial untrusted run completes. Step 3, the attacker doesn't do a thing. The poisoned cache just persists silently in your infrastructure over the weekend. Step 4, Monday morning, a maintainer merges code, triggering a fully trusted job. Step 5, that trusted job dutifully restores the poisoned cache and executes the payload. Privileges escalated, and the attacker just gained access to your production deployments. The untrusted run is over. The poisoned cache is not. This is a vital concept in pipeline security. State persists across the trust boundary. The attacker is long gone. Their pull request might even be closed and rejected, but their malicious cache is sitting there like a time bomb, waiting for a highly privileged release job to detonate it. To address these specific vectors, GitHub made several crucial platform updates in 2026. On June 26th, they implemented a read-only cache policy for qualifying untrusted or default branch context triggers, which effectively closed that common cache write escalation path. Then, on July 16th, Actions/Checkout version 7 was released, actively refusing common forkhead checkout patterns when running in a pull_target context. A few days later, on July 20th, 2026, this checkout enforcement was backported to all supported checkout versions except version 1. Operationally, if you're using floating supported major tags, you receive this protection automatically. However, older pinned versions require a manual update, which SREs need to track closely. GitHub blocks the common path now. Common is not complete. It is absolutely critical to understand what this means for your infrastructure. Workflow execution protections operate as a public preview policy layer. They provide an excellent safety net and defense in depth, but they are not an architectural fix. You cannot rely on them as your primary defense to somehow magically transform a fundamentally flawed, privileged workflow into a secure sandbox. Because these platform protections have distinct limits. If your workflow ignores the checkout action entirely and uses manual Git or GitHub CLI commands to fetch untrusted code, the checkout protections are bypassed. If you use other privileged events with unsafe YAML designs, like an issue_comment trigger that parses the comment body directly into an inline shell script, you're still completely vulnerable to command injection. And, as we just covered, if you are running unupdated versions of the checkout action, like version 1 or an older pinned SHA, the mitigations simply don't apply. The checkout updates don't eliminate all PON requests. The rule remains unchanged. Do not execute untrusted material in a privileged context. So let's rebuild this workflow architecture the right way, cleanly separating our duties. For your untrusted jobs, meaning any job that must build, compile, install dependencies, or test pull request code, use the unprivileged pull request event. Configure explicit read-only permissions for the token. Ensure absolutely no repository secrets or deployment credentials are given to this job. Use ephemeral runners. And finally, treat any output from this job as completely untrusted data. For example, if your untrusted job uploads a test coverage report as an artifact, your subsequent trusted jobs shouldn't blindly execute scripts contained inside that artifact. Now, for your trusted jobs, the ones handling metadata, labeling, commenting, or deploying, you can safely use pull request target, but you must never check out the pull request code into that context. Maintain incredibly narrow permissions, granting exactly what the metadata task requires and nothing more. When dealing with actual deployments, strongly prefer short-lived OIDC credentials over long-lived static cloud secrets. And importantly, pin all your third-party actions to reviewed, full commit SHAs instead of floating tags. This guarantees you aren't silently pulling in compromised upstream code that could poison your trusted environment. To ensure your pipelines stay secure long-term, you need a reusable framework. I use this mental model every single time I review a PR that touches CI/CD. For every step in your YAML, evaluate it carefully. First, who controls this? Is it coming from the base repository, a contributor fork, a downloaded dependency, or a restored cache? Next, what privilege exists right now? What are the token permissions? What secrets are loaded? And what kind of runner access do we have? Finally, what crosses the boundary? Is it checked out code being executed or shell expanded input being processed? If contributor-controlled material is executed where trusted privileges exist, you have to separate those jobs. When you go back to work and look at your pipelines, ask yourself, who controls the code or input? What privileges exist in this job? What crosses the boundary between them? If you found this audit framework helpful, be sure to subscribe to DevOps Corner for more deep dives.